This is IQE 6, and this is the conceptual question. You purchased a burger from Wow Cafe and added some ketchup to your burger from the ketchup dispenser. What kind of pump is this, and explain how this works? The answer is, this is a net positive displacement pump. There's an inlet where the ketchup can come into some volume inside, and there's a piston that moves and can decrease or increase the volume. And it increases the volume. As it increases the volume, it will suck the ketchup in through the inlet, and when it decreases the volume, it will push the ketchup out the outlet. And also, there are spring-loaded valves on either side that keep the ketchup from going out the inlet when the piston moves up and lets the ketchup only go out the outlet. It also keeps it from coming through the outlet when you move the piston down. So basically, the net positive displacement pump allows the ketchup from a low pressure source to get pumped to a higher pressure receiver by decreasing the volume of the chamber. It mechanically forces it to move. For the calculation question, I was studying at Arthur Lakes Library on Sunday, where the ambient temperature was 15 degrees Celsius and the wind was blowing at 10 meters per second. I accidentally dropped my steel pencil, which has a diameter of 6 millimeters and a length of 19 millimeters. Find the terminal velocity of the pencil. So, we know the length and the diameter. Divide them, we get 13.6. Looking at table 11.2, we get a drag coefficient of 0.9. First, though, we check the Reynolds number to see if the Reynolds number is high enough in order to check table 11.2. And it's 2.76 times 10 to the power of 7, which is very high, which is why we're able to get our drag coefficient from table 11.2. Properties, we have density of steel pencil. The density of steel is 7,900 kilograms per meter cube. We have density of the fluid, which is the density of air at 15 degrees Celsius, which is from the saturated air properties, and the viscosity is also viscosity of the air at 15 degrees Celsius from the saturated air properties. And we have the gravity. We assume incompressible constant gravity and adiabatic. So we form a momentum balance, and we know that that is weight, which is mg, minus the buoyancy force minus the drag force equals dm over dt. dm over dt, as we know, is mdv over dt plus v dm over dt. dm over dt is 0 because the mass is not changing, and dv over dt is acceleration. We know that the volume of a cylinder is pi d squared over 4 times the length. So now, we know that the terminal velocity is the point where the acceleration is equal to 0. So if acceleration is equal to 0, the right term, everything on the right, will be equal to 0. So we'll be able to rearrange this to find the drag force. We know that the relationship between drag force and drag coefficient is this equation. So we plug in what we have for the drag force into this equation to get this here. So now, we rearrange this to solve for terminal velocity. We plug in all our numbers, and I see our units. We end up having 2670.7 meters squared per second squared. When you take the square root of that, you get 51.7 meters per second. And that is the terminal velocity. The terminal velocity is high because the density is very high. When density increases, the drag force increases, so the velocity increases. Thank you.